Okay, so what's important to remember about L and U is that L is a lower triangular matrix with ones on the diagonal. We can create a little icon like that. And then U is an upper triangular matrix. Now, what we usually do is we start with matrix A, and as we compute, we overwrite it with L and U. And when we're then finished, we have U in the upper triangular part of A. And because L has ones on the diagonal, we can store only the strictly lower triangular part of L below the diagonal, right there. That means that we can overwrite A as we go along. Okay, so how do we do that? Let's erase this. Now, these properties about L and U, we're kind of going to keep in the back of our mind. Okay, so we're going to be a little sloppy and not express that as part of our predicates. Now, the first thing we want to do is come up with a precondition and a postcondition. Obviously, the precondition is that A contains its original contents, A hat. And the postcondition is going to be a little bit more complex because somehow we have to be able to capture that A has been overwritten by L and U. So the way I'm going to denote that is that when we're done, A contains L and U. And I'll create this notation, this backslash between the two, to kind of indicate that L is really sitting below here and U is sitting above here. Alright? And then, what has to be true about L and U? Well, if you multiply L times U, you should get back the original contents of A. Okay? Precondition, postcondition. Now, remember, in order to come up with a partition matrix expression, we needed to think through how we inherently march through the arrays. Okay? Think back about how we marched through the arrays when we were talking about eliminating equations. That may be a good hint. Think that through.